Welcome back to the Mad Scientist Podcast. Sorry for the long delay in episodes. I've been in San Francisco for a conference, presenting some of my slightly less ghost-related research work, and I'm basically writing this episode in snippets as I tour the area, go to technical sessions, and eat a comically large amount of Mexican and Japanese food. I wanted to have one ready before leaving, but in between getting final poster drafts ready, planning to help out at the conference itself, and making sure that the students from my lab that came with me to this thing didn't die falling off cliffs or wandering into traffic, it's been a crazy few weeks. One really cool thing that's happened this week, though, is I've been featured as a guest lecturer in the webcomic Surviving the World, published by my friend Dante Shepard. So if you want to get a look at what this mad scientist looks like, head on over to the website and take a look. I'm working my way towards being mistaken for Bigfoot when I go hiking, so let me know how you think that's progressing. One other thing I've got to mention this episode is the results of the recent election in the United States, my home country. Now, regardless of my political views, my scientific knowledge and training makes these election results pretty chilling. Battling climate change is one of the primary areas of interest for me and top applications for my work. And the stuff I work on in my real job focuses on capturing and converting carbon dioxide, as well as green energy and nanomaterials for energy systems in general. The election of Mr. Trump hurts these goals without question. He's a climate change denier, and a foe of science generally, not to mention his even more shockingly insane running mate, believing in most of the wacky shit that the majority of the world left behind after the Renaissance. Being religious is a personal choice and conviction, one that scientifically and philosophically I don't believe that we can touch ultimately. But Mike Pence's continued refusal to keep the world of religion separate from the world of political affairs and scientific progress is a really hard thing for me to accept. I'd be lying if I didn't say that this election feels a little bit like a slap in the face of my career and love of science generally. A rebuke of the intellectualism that has created and continues to create a huge amount of jobs and status for the United States. Whereas we used to strive to become scientists and astronauts, telling our children that to go to school and learn was something that would make their lives better, I fear that this country has begun to polarize and politicize learning and scientific thinking. I know I'm not the only scientist who has relatives that believe their work is a naive millennial fantasy, or that the specialized training I've received to become more knowledgeable in the fields that the general public may not even know exist has actually turned me into a secret Bolshevik, hiding my communistic tendencies behind a veil of environmental and social concerns. Striving for knowledge and creating things was once considered a patriotic duty. And yet, in today's world, the institutions that create the materials and technology that make the United States a center for advancement in the world are looked upon with distrust. Those intellectuals with their noses in the air, looking down from their ivory towers on the real America, whose jobs are going overseas and whose kids are joining the military and dying to protect countries that they'd never even go to otherwise. But science and the heartland are connected, with the advances made in the lab helping to make farming more efficient, or lessening our reliance on foreign oil so gas prices can stabilize, or keeping you out of the coal mines that poisoned your land and gave cancer to your grandparents, or creating new materials that protect your kids when they go overseas to fight for all of us. The United States needs science and scientists, and I implore my listeners to not forget just how much of this country's prosperity and ingenuity has come from the same places that we are now being told to disdain and fear. Frankly, the jobs that people are worried about having left this country have left here for good. Technological advancements have many after effects, and some of these include automation and improvements in efficiency that make having a factory producing 100 units a day using human labor no longer an option. But scientific advancement has before and will continue to create jobs. I have faith that our country will continue to rebound from the economic downturn, but I hope that our fear of job losses in places primarily taken over by robotics and automation will not end up stifling progress that could create work for people still hurting from the Great Recession. Finally, and this is the last serious word I'll have on this election, is the issue of immigration. Besides the people coming here to make better lives for their families, or to escape persecution in their home countries, there are a huge amount of immigrants here making important contributions to fields such as medicine, energy, infrastructure, aerospace, transportation, and many others. During my PhD, I have met uncountable numbers of phenomenal, hardworking, kind, and intelligent people who have come to the US to learn and live as master's or doctoral students. To think that some of them are now afraid to be sent back to their home countries before their studies can conclude, or that the already difficult task of staying in the US after graduation may actually become more difficult because of an election, is heartbreaking. We should be embracing these students who come here to learn, letting them stay in this country to use their talents and knowledge to improve all of our lives if they want to stay. To allow it to continue to be so difficult for them to work in the US, and to think that it may actually get harder, is ridiculous, and to be absolutely blunt about it, insanely stupid. If you're smart enough to get a PhD or master's in the United States, you should be a desired asset to this country. Alright, end political rant, begin paranormal science wacky stuff rant. One hilariously misunderstood part of science in the popular mind is quantum mechanics. People love to talk about it, philosophize on it, and come up with ways that it lets them skirt around all sorts of hard scientific truths that seem to make some of our more creative paranormal claims fall on their heads. But quantum physics really isn't all that complicated, at least if you take all the scary math out of the way. Conceptually, quantum is something that pretty much everyone can understand, at least I tend to think so, and it's something that sort of works very well with analogy, as opposed to some other less popularly talked about but more difficult to explain fields of physics and chemistry such as thermodynamics. I mean, everyone knows what an electron is, but if you can find more than one person in a room of scientists who is really confident that they understand how fugacity works, then I'd bet you'd wandered into a Nobel Prize winner's luncheon or something. And even then, I bet a few of them are faking it. Quantum mechanics has been used to explain all kinds of weird things, from teleportation to multiple but distinct universes to ghosts and angels and heaven and hell, and of course the question of aliens and time travel. The breadth of paranormal stuff that has been explained using what began as a way to understand why experiments with light beams weren't working out the way we thought has really only increased with time. But is quantum mechanics a good fit for any of these paranormal claims, or is it just the next in an unending line of novel scientific fields used to justify our magical ways of thinking? Do ghosts made out of quantum mechanical stuff hold any more water than ghosts made out of spiritual stuff? What the heck is quantum mechanics anyways? All of this and more in this week's super special mega episode.
Welcome to the Mad Scientist Podcast! Tonight's episode: if understanding quantum mechanics makes you a wizard, then consider me David Blaine!
To begin with, I think a general outline of quantum mechanics, what it is and what it isn't, is important. So, our understanding of quantum mechanics really comes from our understanding of the atomic structure of matter. This effort began in ancient Greece, really, with philosophers such as Democritus positing various basic pieces that make up everything. Some argued that these things were made up of elements like fire and water, earth and wind, but others got pretty close to how we currently understand things. Democritus, in fact, thought that everything was composed of fundamental particles that he called atoms, which made up everything in different combinations. He also thought that things contained primarily atoms and then voids where atoms were not. I mean, he got comically close considering that this was at the same time that the average citizen was drinking wine laced with lead because it made the drink taste significantly sweeter. Anyways, atomic structure didn't get too much more refined until the time of John Dalton, who in 1803 proposed what we term as an atomic theory, basically saying that the elements were composed of discrete packets of mass and could be described by their mass primarily. Dmitri Mendeleev then used a similar sort of idea to develop the periodic table in 1869. He grouped the elements known at that time together into 7 groups with similar sorts of properties, only to find out that these properties seem to periodically vary with their mass. This is partially why the periodic table is set up the way it is, and we now know that this periodic variation is actually caused by the changes in their electron density and the number of protons and neutrons the atom has. So, okay, In 1873, James Maxwell then proposed that there must be some electromagnetic part of the atom as well. And in 1879, Sir William Crookes all but proved this by the use of a cathode ray tube. A cathode ray tube is basically a long tube where you could generate electrons to shoot at a surface by electrically stimulating some piece of matter that was held on one end. He used this to see that whatever was coming out of the tube seemed to be negatively charged, and that the flight path seemed to suggest that there must have some mass to this charge as well. This is really one of the first experiments where we started looking at electrons. G.J. Stoney then proposed that these pieces must be discrete particles, and he called them electrons. After the discovery of the cathode ray tube, and specifically that atoms seemed to give off energy when certain sorts of other energy were supplied to them, things really started to take off. People like Rutherford, the Curies, and Röntgen, to name a few of the big ones, started making tests of radioactivity, finding that one could also remove positive or neutral charges from an atom. In 1900, Max Planck postulated the idea of a quanta, or discrete piece of energy, that could be removed from this atomic center. These were eventually moved to basically describe all pieces of the atomic structure, really, so everything is now pretty much considered to be a quanta of energy. The next really big change happened in 1911 with Ernst Rutherford again. He used what is now known as the gold foil experiment to find that the atom is composed mostly of empty space, with a very small but heavily charged center. To do this, he shot electrons at a very thin film of gold, and found that the majority of the electrons just shot right through to the back, suggesting that they were not coming into contact with anything. However, in some places the electrons would bounce back seemingly at random, suggesting that they were hitting a positively charged mass. At this point, we all have some vague idea about what an atom looks like, what its structure is, and how it operates. But no one had really developed a working model of the atom, something that could explain all of the radioactive and electron-shooting properties used to find out so much about atomic structure in the first place. Finally, Niels Bohr developed a working model in the early 20th century, which basically described the atom like a solar system. In this model, you had your nucleus, consisting of protons only at this point. Around the nucleus circled electrons in concentric rings, much like how the planets circle the sun in different orbits. Now, the electrons would be more strongly held to the nucleus the closer their ring was to the nucleus itself, due to the fact that electrons are negative and the nucleus is positive. It was also found that each ring contained different numbers of electrons, based on how much energy it took to actually strip away electrons from the rings. So the ring closest to the nucleus had 2 electrons, the next ring out had 8, then 18, with increasing numbers in each ring as it kept going out. This in totality is known as the Bohr model of atomic structure. What made things weird was that this model couldn't explain certain atoms, specifically those that had higher atomic numbers, which, as we all remember from the episode on nuclear monsters, means higher numbers of protons and neutrons. And this model could also not explain the transition elements, which showed electrically conducting properties. So when something is a transition element, it has electrons that are actually lower in energy than those in the highest subshell, than in the Bohr model would be the farthest away. In other words, when studying how electrons are removed from a transition element, one may find that more electrons are easily removed than should be possible from just the highest concentric orbital. Another problem was that Bohr's model applied the same physics that we applied to planets circling a star as to electrons circling the nucleus. So for example, when a planet circles a star, it is being accelerated and deaccelerated by the gravity of the star, with momentum being converted into potential energy and vice versa as it orbits. Thankfully for us, the planets are in a special sort of orbit, where they aren't being pulled any closer. But electrons aren't just losing momentum around a nucleus. They're also losing energy waves in the form of radio emissions. So according to Bohr's model of these electrons, as they spin around the nucleus and lose radio waves, a mathematical model of their orbiting the nucleus and the loss of energy via radio wave emission suggests that they would have to eventually collapse into the nucleus itself. There just isn't enough energy to let them keep going in the same way that a planet in equilibrium with a star can. But electrons don't fall into the nucleus at all. So this was a pretty big problem for Bohr. Really, the primary nail in the coffin for Bohr's model were the various experiments also going on in physics laboratories at the time. Bohr developed his model around 1915 to 1922, and in the ensuing 10 years, we learned a huge amount about the atom and its pieces that basically made his model completely obsolete. First off, de Broglie discovered that electrons actually seem to exist as both waves and particles simultaneously. And even weirder, they seem to change from one to the other depending on what sort of experiment you're running. The most famous example of this sort of result is what is known as the double slit experiment. So, we're going to do something that Einstein used to call a thought experiment, which, by the way, Einstein was working during this time too. In fact, one of the coolest, battles of the scientific geniuses, heavy metal music constantly in the background, rivalries, was between Einstein and Bohr. Although really, it was more of a friendly bromance where two competing geniuses had differing opinions on atomic models. You know, that classic brain meets brain love story that we've all had in our lives so far. Einstein, in fact, said in a letter to Bohr, quote, "Not often in life has a human being caused me such joy by his mere presence as you did." End quote. Einstein loves Bohr. Alright, so double slit experiment. Basically, imagine you have an electron gun set up so that it will shoot at random directions forward over a certain angle. So the field of possible shooting locations goes a little bit to the left and a little bit to the right of the center position. And with each shot, it will go in a straight line path in one of those directions. Up to this point, we knew that electrons went in straight paths because we could shoot them through the use of cathode ray tubes at photoluminescent pieces of film. Basically a black surface that will turn white once it's hit by an electron, much like current photograph films. So we set up our experiment where we have our electron gun on one side, and it's shooting towards a photoluminescent film on the other side of the room. When we shoot the gun at the film, we see dots of light where electrons have hit the film, and given enough time, all of these little dots will merge together to form basically a bright horizontal line on the film surface. This line represents all the places where electrons can hit the film. Now imagine that we put a piece of solid film that electrons can't pass through in front of the gun. We would imagine that we won't see any dots on the other side of the film, right? Alright, so now let's say we put two thin slits in the piece of film, so that electrons can pass through them when the gun is turned on. What should we expect to see on the other side of the film? Well, if electrons act like particles, as we used to believe, then they should be stopped everywhere except where the slits have openings. So on the other side of the film, we would expect to see two bright spots behind where the slits are, and no spots anywhere else. This can be visualized like shooting paintballs through a window at a wall. And so we expect that the big paint splotch will be visible only in the area of the wall behind the window. But if we turn on our electron gun and leave the room, what we find is not what we expect. Instead of finding two areas of bright film behind the slits, we find that there appear to be bright spots going across the film at regular intervals, even in areas where the slits are not present. So to use the paintball analogy, we find that the walls we're shooting towards doesn't have paint only in the place where the window is in front of it, but instead seems to have paint in zones, like every foot apart across the entire wall surface. It turns out that the electrons are acting like a particle when they are shot directly at the luminescent film, but are appearing to act like a wave when the screen with the slits is placed in front of the gun. Why do we say that they're acting like a wave? Well, the main reason is that on the film they appear to behave periodically, showing spots where electrons have hit a certain distance or wavelength apart from other electron-dense spots. So visualize a wave in your mind. It goes up and down periodically, and every top and every bottom of the wave is some distance apart from another top or another bottom, and this distance is what we call the wavelength. Now imagine that the wave was coming towards some surface, so that the wave going up and down is going up or down from the surface itself. In other words, the wave is perpendicular to the surface. So as the wave travels along the surface, it goes up to its highest point, then down through the surface towards its lowest point, then back up and over again. If the wave was of the type where it would make some mark on the surface, Where would we see the marks? Well, only at all of those points where the wave hits the surface, which are going to be a wavelength apart from each other. This gives us the exact sort of image that our two-slit experiment resulted in. There are periodic spots of bright film where the wave hits, and dark film where the wave is either above or below the surface. But this is insanely weird, right? If we use our paintball analogy, it's like the paintball acts as a solid spherical particle when they aren't going through the slits. But the moment they start going through the slits, they begin acting in a weird wave-like pattern. Even stranger, this suggests that the electron or paintball in our analogy doesn't seem to have a fixed position at any given time. Think about it. As soon as it goes through the slit, it no longer follows the trajectory that we would imagine it should. Instead, it takes on this wave pattern and can appear at any of the positions in our wave at any given time. The waves we're talking about aren't like, okay, the electron is going up and down and the wave's going up and down. What we mean is that the electron itself is the entire wave, taking on that pattern as it propagates through space. As you can imagine, this was a pretty mind-blowing result. Especially the fact that it appeared that these particles were behaving differently if they were constrained in some way. So in our two-slit experiment, the electrons behaved as we thought they should if we didn't try to limit the possible place where they could go through the film. But once we added the shield with the slits in it, the particles began to act like waves once they passed through. This was really intriguing, and so one scientist, Werner Heisenberg, sought to try and figure out what the heck was going on here. And it wasn't just Heisenberg, of course. There were loads of scientists working on this, but Heisenberg came up with the catchy uncertainty principle, so he's one of the best remembered ones. First off, we come up to something called the observer effect. In any experiment, it's impossible to observe a phenomena without changing it in some way. And this gets more and more important the smaller and smaller the things we're trying to figure out gets. This is because to measure something, we necessarily must perturb it in some way. The classical example is that of measuring the air in your tire. To measure the air pressure directly, such as with a pressure gauge, you necessarily need to remove some air from the tire to hit the gauge. This will affect the pressure in the tire, and thus you have changed your system by trying to observe it. This effect in itself is one of the primary ways in which the paranormal turns quantum mechanics into ridiculous pseudoscience. So just to start with, let me state this clearly. The observer here does not need to be conscious. In our tire example, the observer is actually the pressure gauge, not the guy holding the pressure gauge, which I don't think even the most ardent paranormalist would argue has, a pressure gauge with some kind of intrinsic consciousness. In our two-slit experiment then, the observer would be the slits themselves, since we're trying to measure the position of our electrons by limiting where they can possibly be. The observer effect is the basis of the famous Schrodinger's cat problem. Let's imagine a cat in a box with a radiation-emitting source that upon release of some radiation can cause a vial of poison to break open, killing the cat inside. There's a 50% chance that the vial will break when the radiation triggers some event, and a 50% chance that it won't. Alright, so then if the box is closed, is the cat alive or dead? We can't know, and so must state that the cat is basically in a weird position where it is, for all intents and purposes, both alive and dead. Once we open the box, we are disturbing this system, and so we're setting the state within the box by our very observation. It's a weird experiment, and not one that I would suggest you try at home. Anyways, besides the observer effect, we also come to the problem that in order to measure certain quantum properties, we necessarily alter other properties. For example, in order to find out the position of an electron at any given time, we need to either hit it with some other particle, such as a photon or something, or we need to limit where it can actually go. But by doing this, we introduce uncertainty to some other coupled variable. For example, position and momentum are inherently linked in this way at the quantum scale. To try to understand this better, we can look at the mathematics of the thing, because they are mathematically linked together in the wave functions that describe quantum particles. So this can get really confusing and mathematical, and I'm going to try to make it simple, But a good example is our description of a wave before. When something mathematically is described by a wave function, it means that it can have an infinite number of possible solutions, which are linked together through some mathematical relation that is basically like the wavelength. So think about a wave that goes up to its maximum position, then down to its minimum position. As we go up and down vertically, we're also moving to the right horizontally as we draw our wave graph. So do it in the air with me, right? We go up, and then we go down, and then we go up, and then we go down. And as we go up and down here in our wave, because the wave isn't touching itself, we have to move it out horizontally. So now let's start putting some numbers on this thing. Let's call the maximum height that the wave can get to +1 units of height. And the trough that we draw at the bottom we'll call -1 unit of height. This means that our wave goes up to 1, then goes down through 0 to -1, then back up through 0 to +1. Okay, well now let's put some values on the horizontal axis as well. So let's say that the first time the wave hits +1 height, we'll call this 0 horizontal. Then when it hits 1 again, we call this 1 horizontal, then 2 horizontal, and on and on. Alright, so we have a graph where the wave is going up and down, and every time it hits +1, we add another 1 unit to the horizontal axis. Now, I can't speak for everyone listening to this podcast, but I know at least for some of my listeners that I know personally, this is the first time you've drawn a graph in like 15 years, so congratulations. Welcome to my nightmare. Well, let's say that I want to know where on the horizontal axis my wave will be at the maximum height. So +1 unit in height. What is that horizontal axis value? If we just imagine our wave, it turns out that there are an infinite number of possible horizontal values, right? It's going to be +1 at horizontal 0, at horizontal 1, at horizontal 2, and in fact will be equal to 1 at all values of the horizontal that are whole numbers. Because I'm trying to describe a wave, something in physics that we call a wave function, I can have an infinite number of possible solutions to get the same result in height. With all of these solutions, though, being a certain set distance apart from one another. This is the extremely simplified and definitely overly confusing mathematical sort of version of the uncertainty principle. If I know what my vertical height is on my wave, I don't necessarily know my horizontal position. In physics, this sort of problem happens with momentum and position of quantum particles, for example. So if I measure the position of an electron or photon, I won't be able to definitively know the momentum of that particle, because the momentum and position are related by a wave function, just like the height and horizontal distances of our simple version above. So if I set the position, I end up with an uncertain momentum, and vice versa. This is known as wave function collapse, because by setting one value of the relationship, I end up with a solution that gives many equally probable values, just based on the properties of waves themselves. This means that we can never know the exact momentum and position of quantum particles, as well as some other linked variables as well, which also show this relation with one another. Now, this isn't just some mathematical weirdness or formalism. We're using math to describe what we actually see in the lab. So, wave function collapse is a physical phenomena that mathematically we can describe nicely using wave functions. But that's really scary though, right? It means that things inherently are not deterministic, but instead that the universe, in some ways, operates on probability, because we can never actually define certain variables all at once. It's like saying that if I know how many apples I have, I can't know how much applesauce I can make. Things are getting real weird now for physics. This issue of the uncertainty principle brings up some of my favorite paranormal ridiculousness, one of which is based on what was initially a mathematical formalism to fix that scariness that a probabilistic universe brings out in us. This is the many worlds hypothesis, postulated by Hugh Everett III in 1957. Basically, this states that since we can't measure something without affecting the thing we have measured, it does not make sense to talk about the final definite state that a measurement will result in. Instead, we can only talk about the relative states that the measurement could result in. So for physics to work, we need to talk about all of the possible relative states as one total determinant state. So like in Schrodinger's cat, We don't talk about the cat being either alive or dead, but we can talk about the final superstate, where it's one or the other. Basically, this is a mathematical formalism creating what appear to be alternate worlds that represent each of the potential relative states that can occur. So the cat is alive in one and dead in another, and they branch from one another at the point of observation. But this doesn't mean that we're making alternate universes or something. It means that mathematically, we can treat the two things as part of one definite state, and so no longer need the probability stuff that other quantum things, like Heisenberg's view, require. Incidentally, there is an insanely good documentary on this guy, and what a destructive effect his theory and people's misunderstanding of it had on his life. Produced by his son, who is the founder of one of my favorite bands, the Eels. It's called Parallel World, Parallel Lives, and I strongly suggest it to any science history nerd or lover of really great music. So, alright, back to atomic structure. To try and fix the model that Bohr came up with, and to include all the craziness we just talked about, Erwin Schrödinger came up with his model of the atom, a variation of Bohr's that placed electrons into clouds of most likely position, utilizing his work on describing electrons in probabilistic wave function positions. So instead of an electron moving in a very clear causal path around a nucleus like a planet orbits a sun, electrons were instead visualized as being present in what are now called orbitals. These orbitals are basically zones of highest probability, where the electron is to be found about 99% of the time that you look, where the electron has some unknown momentum as well. This is pretty much how we view electron clouds today, and the atomic model. Schrödinger came up with his model in the late 1920s to the late 1930s. Okay, so that was a not-so-brief primer on quantum mechanics and the history of quantum. As we understand things now, all things that are at the quantum scale, so about the size of electrons, behave as wave particles. They appear to change depending on how they're measured, because certain properties that they take on cannot be known simultaneously, such as momentum and position. And most importantly, this uncertainty means that physics at the very small scale is not determinate in the same way that physics at the macro scale or the observable scale of things are. You cannot tell with 100% certainty where an electron is or how fast it's going to go at the same time. But you can do that with something like a car or a baseball. This is what is meant when we say that classical physics breaks down at the quantum scale. But notice that things behave just as we expect them to if we get just a bit bigger than quantum particles. An electron is about 1/1000th the radius of a proton, which is about 0.84 times 10 raised to the negative 15th meters wide. Just for your own visualization here, a human hair is about 17 times 10 raised to the negative 5th meters. So protons and neutrons act basically like solid balls of mass, just like a baseball but much smaller. This means that it doesn't take a whole lot of extra size to get out of the quantum world, and so attempts to normalize quantum properties to real-world problems or issues are not usually very well founded. So what are the sorts of paranormal things that quantum mechanics gets applied to? Probably one of the most common is that the weirdness we see in quantum mechanics can somehow be used to explain free will or consciousness. The argument goes something like this. Since the major attack on free will is that the particles that seem to make up the underlying parts of the universe are deterministic, so they don't show any ability to make free choice decisions, then it doesn't make sense that bigger objects such as animals or humans would have that ability. This is a form of the argument that items must have the same properties as their parts, something that we've talked about in other episodes. But we know that that isn't really the case, right? There are intrinsic properties to things that seem to emerge when things are put into combination, that are not present or intrinsically part of the underlying pieces. Are the atoms that make up a strawberry red? Do the subatomic particles in a cheeseburger taste better than the particles that make up a plastic bottle? Do the particles of the brain need to have free will or a soul for our minds to exist? I think the problem with this sort of argument generally is that it requires that the pieces have the same properties as the whole, something that is woefully insufficient when explaining the world. Things do seem to have really, very real emergent properties, and so to try and explain them away at the subatomic scale is misguided in my opinion. Some philosophers would argue that the solution to this is a sort of supervenience, a system where the sum of the parts makes something that contains properties that are not present in the individual pieces. This is the kind of argument I just made above, more or less. But for free will, people like to throw in quantum physics as a kind of, non-supervenient, scientific-ish explanation of free will. So because particles seem to not necessarily be fully determinate, for instance, their position and momentum are not determinate, but they are probabilistic, this leaves some wiggle room for their combinations to also be non-determinate. In this view, free will comes from the quantum effects of macromolecules that I guess only ever occur in the brain because we don't really see them anywhere else. But as the explanation of quantum mechanics talked about earlier, most of the weirdness of quantum comes due to the complicated relationships of some of the properties of quantum materials, such as momentum and position. So we really do know a huge amount about these variables, including the fact that we can't know the one exactly at the same point that we know the other. So I can never really get my mind around the idea that free will exists in this somewhat complicated mathematical relationship between properties. Free will seems to require something completely separate from physical laws, because it allows us to work outside of their sphere in some way. The same thing for consciousness. I mean, I can imagine that I'm flying, for example, but I can't really ever fly as I imagine. I can also dream and have intensely vivid hallucinations, or get super drunk and think that I'm far more charming than I really am. Does quantum mechanics really explain all of these extremely complicated aspects of life, and our intake of data even from our surroundings? The free will or consciousness stuff almost always inevitably relates to ghosts. This is a quote from a blog that I found online, one that I hope the author will not be mad that I am quoting here, and that goes for all of the blog posts that I'm going to be quoting in this one. It says, quote, "Mythology would tell us that ghosts are the lingering spirits of the dead. Balderdash. Ghosts are not at all the spirits of the dead. They are not, in fact, spirits at all. A ghost is, put simply, an impression upon the subatomic weave of the universe, created via strong emotion of a sentient observer. This means, in other words, that ghosts are not the disembodied personalities of the dead, and in fact, they can be spirits of the living. To understand this phenomena, one must first grasp one of the most fundamental principles of quantum mechanics. Observation changes the subject being observed. The simple act of observing or measuring a particle forces it into an energy state. Unobserved, a particle may take any energy state available to it, but when a sentient observer is introduced, the particle becomes locked. Ghosts are created when the observer's emotions create a semi-permanent indentation into the quantum tapestry of the universe. Like the scent of burned toast that remains long after the offending bread is discarded, ghosts are impressions of emotions that remain long after the cause has been resolved. Ghosts, therefore, are formed not from the dead, but from the living in their interactions with the world around them. The recording of events within the subatomic weave gives rise to an afterimage, and depending on the intensity of the emotion and the permeability of the quantum state, different types of ghosts can be created." End quote. So I suppose the argument here is that ghosts are somehow emotionally leaving behind a blueprint on what the author calls the subatomic weave of the universe. First off, what the heck is a subatomic weave? I suppose that what is meant here is the underlying fabric of the universe, something like space-time as Einstein described it. Interestingly, we do know that certain things can interact with space-time. For instance, extremely massive things cause changes to distort space-time locally and create what we feel as gravity and time dilations. But nothing of this sort has ever been observed on the subatomic scale. And frankly, why again are we thinking that emotions in some way create effects on our subatomic atoms? How is it that atoms and emotions interact? And if they can in the way that this person's claiming, then could someone with extreme emotional raw energy or something become telekinetic? I mean, this is another sort of argument here, that if somehow we could only affect the quantum states of matter, we may be able to cause seemingly magical things to occur. So we could get things to levitate if we could alter space-time at the quantum scale or something. Or how about walking through walls? Well, if you can get your atoms to vibrate at the right frequency, then quantum wave-particle duality will allow you to just move right through another solid object, just like how our electrons seem to move through the wall in the two slits experiment. shooting fire out of your hands. Merely a matter of altering the energy released from electron orbitals to increase to such an extent that you begin to combust. I mean, a lot of these explanations are currently found in both the pages of X-Men and in some of the more die-hard quantum allows for paranormal stuff communities on the web. Anyways, this author falls into the trap of thinking that an observer is a conscious thing. Observers are literally anything that can make an experimental observation, which sure at the macro scale could be your eyes, but at the quantum scale are most often photons. So do the photons that observe other quantum states then see how emotional the surrounding photons are, and so make a lasting memory? Furthermore, how is it that they create a lasting effect? In other words, if we observe the position of a photon at some time, we do set its position in one way of thinking. I mean, beforehand we had only a probability, but now we have a set position, and simultaneously an unset momentum. Fine, but if we then let the photon go back into the cloud of other photons, will it act any differently because it has previously been observed? Well, no, of course it wouldn't. At least I can't imagine why it would. It's almost a form of the gambler's fallacy, right? That the history of a set of probabilities can affect the outcome of the next game. Like, I've lost 10 in a row, so I'm due for a big win here. But instead of it being like gambling, what you're now thinking of is, well, this atom of hydrogen used to be part of a person that was, severely emotionally damaged. So this hydrogen atom made an effect on the quantum particles in the surrounding area, and now they're a ghost? This is a hard one to get my mind around. I think ultimately they're applying a scientific argument to what is actually a magical way of thinking. People have thought that ghosts were the leftovers of our consciousness since forever. And they're just using the easy quantum mechanical argument to try and make sense of this non-scientific idea. Another version of this argument is that ghosts are simply beings that exist in another plane of reality, one that is accessible because of the ability of quantum mechanical objects to seemingly move into and out of reality. But again, this is a misunderstanding of what is happening in quantum mechanics. The main argument for this is the double slit experiment, where it looks like the quantum thing can go literally anywhere it wants to in between the slit and the fluorescent film. But that's not the case at all. It's just that now it is behaving like a wave. I mean, we can write out the math to tell us where the particle can hit and where it cannot hit. There's no reason to think that it is likely for a quantum thing to just jump from one side of the universe to another, for example. Let alone that the billions of quantum particles that make up something as big as a human would do so simultaneously, or with any directed energy or something. Another version of this argument goes as follows, and this one's from a forum post that I had read a while ago and bookmarked. Quote, "When people say they have crossed over or passed away, I often question, cross to where? Does anyone really know where the spirit or this energy goes? Most religions differ on this subject, but many agree that an energy of some sort moves on. What is this energy, and how does it interact with our world or the next? I propose a radical but possible theory that deals with quantum physics and an infinite interdimensional multi-universe. I have heard and analyzed enough EVPs and other evidence over time to suggest that this is a possibility. For example, EVPs from investigations where pictures are being taken of disembodied voices that were recorded saying things such as, 'I see flashes' or 'who's there?' There was a case several years back when a business owner here in Ohio had several employees seeing an apparition of an Indian chief. A psychic medium was brought in to assist with communications, and the spirit of the Indian chief was asked several questions as to name, time frame, and one in particular that really interested me. Do you see this building? The answer to which was no. This may suggest that a spirit or the energy of a being passed on may exist in a realm possibly much like ours, but in another dimension that closely parallels ours. The spirit may see glimpses of our existence as energy fluctuations, much like what we may see when we experience an apparition. It may also appear that life may take on a different energy transformation from one type to another, which would be a quantum shift or transfer of this energy to another slice in an infinite multidimensional universe. Maybe not all current living beings transform energies to human-like forms in this alternate dimension, but maybe become something else. An example of this would be a woman in 19th century clothing seen walking the same path in a house or building, following a staircase down a hall, then vanishing into a closed door or wall. The apparition of the woman never interacts with others, and people that see her comment that she appears to not notice anyone around her. The key here is the recorded playback of this energy that usually takes the same path each time it is played back. I believe a quantum event could be the possible trigger that causes the energy to be seen. This apparition is not an intelligent spirit, but rather a recorded moment in time. These recorded moments in time have taken on other forms, such as objects, entire rooms appearing out of place for the time period, and even a story that amazes me still today, of a man hiking in the woods coming to an opening in the forest and sees a valley with a village that appears hundreds of years out of date from the current time period. He watches in amazement as the scene fades from his current reality. These stories and accounts can be found all over the world and date back many centuries to the past. When these shifts occur, they could lend to the possibility of higher EM fields and low temperatures being measured during a manifestation of an entity. Quantum physics supports in theory that time is not linear but exists all at once. This means that we move through the slices of time which appear linear to us because we base our lives on a timeline of events. But if we were to look at these events from a quantum level, things would appear radically different. We are all made of energy. What if the energy we all know as our soul or spirit is released and can freely move to another form or dimension? Maybe this energy is governed by the quantum laws of the universe, and this energy lives on in that plane of existence until another event at some point triggers alternate transformations to other planes of existence. This process may go on for eternity. It is fact that the water molecules you currently drink were many of the same water molecules that the dinosaurs were drinking 65 million years ago. The water molecule, which is two hydrogen atoms bound to one oxygen atom, creates a molecule with incredible energy that can persist for thousands or even millions of years. So water molecules are never really destroyed but recycled or transformed through a chain of events that has always occurred and continues to occur all the time. The universe is a complex system of change, death, and birth of different forms of energy. So again, we're sort of misunderstanding the multiple worlds hypothesis, right? And this idea of interdimensional travel or dimensionality at all, something that we have discussed in previous episodes, has a very tenuous grasp on quantum mechanics generally, and a pretty silly background in physics overall. Dimensions may exist out there that we don't see, but which have some effect on this world. But just like the people of Flatland, it's nearly impossible that we could even comprehend if these things were to actually affect us, save utilizing mathematical concepts to describe things as we do now. Even more interesting is that this idea that quantum mechanics has some memory, or that quantum mechanical objects will behave differently based on how they have behaved in the past. This is a rather subtle form of magical thinking, but one that we all really suffer from in many ways. I know I do. We think that the past of an object leaves some mark on it. So for example, no one wants to buy a house where a murder happened, right? What about keeping old clothes from loved ones, or objects that they frequently used? Or items that belong to a famous singer? Ultimately, the knife that Elvis used to make his evening toast is the same as any other knife at the atomic scale. But we think of them as special because they've been touched by something extraordinary. Religious items, of course, end up with this same sheen. I mean, the number of churches I've been to that claim to have some relic of a saint, only to find that it is something like St. Elizabeth's sewing kit. Actually, kind of funny story about that. When I was a kid, I took a trip to Italy to visit my relatives, and was told that our town is world famous for being the resting place for the bones of St. Nicholas. So at like age 8, I found out that not only was Santa Claus long dead, but his bones are in a town on the southern coast of Italy. Now, if that isn't an awesome beginning to the Christmas season of episodes, then I don't know what is. Anyways, objects don't really have a history in that kind of way. At least molecules and atoms certainly don't, and they don't even have some kind of sentimental history either. I mean, if I take a water molecule and break it apart to its two hydrogen atoms and one oxygen, those atoms won't act any differently than if I took them apart from, say, like sodium hydroxide, which contains one oxygen and one hydrogen. The hydrogen and oxygen will still act exactly the same as if it came from water. Physical matter doesn't behave differently because of what it may have been doing previously. I think the confusion here really comes from the multiple worlds hypothesis, again, as stated earlier. Basically, it appears that measuring something at some point creates multiple different timelines, and so shouldn't quantum objects be affected by which timeline of observation they are a part of. I mean, it's an interesting argument, but one that I think, if we take it to the macro scale, no longer holds any water, as is the case with most quantum mechanical explanations of macro-sized observations. And don't even get me started on the argument about time being circular or linear or whatever. Time is an episode all on its own, but basically quantum mechanics doesn't really have anything to do with time besides, I guess, the fact that time is a variable in most of their mathematical forms. So, can quantum mechanics explain ghosts? Even if they are just impressions on our time left over by the very sad or very angry quantum particles of the past? I don't really think so. I find the argument that ghosts are some sort of soul much more compelling personally, and really much more logical. I mean, ghosts aren't supposed to be physical things. Souls aren't supposed to be bound to our brains. There seems to be something lacking in all these arguments, in that having a soul or ghosts that is merely some effect of quantum mechanics takes away a lot of the really interesting properties one would hope or expect a ghost or soul to have. If we have free will or consciousness or a soul, shouldn't that be more significant than just being probabilistic wiggle room for us to take like one choice versus another? And it really doesn't get rid of the major problem when trying to bring the physical body and the spiritual soul together in the first place. I mean, the issue is that the body doesn't seem to have the properties that the soul has. There is no explanation in modern science for how the particles that ultimately make up the brain can cause something like a consciousness or a soul to exist. To say that it's because of some unobserved quantum mechanical effect that we can't currently explain is in this way this exact same argument as saying that it's a supervenient effect of the brain itself, or just something supernatural that we can't know in the first place. In either case, the problem still exists. How is it that the brain seems to have consciousness, when the atoms that make up the brain do not? And again, primarily what we're doing here is shifting from a magical argument to a magical argument that uses science as a smokescreen. We didn't get rid of the idea of witches moving about objects. We just now assume that it's due to their ability to wage quantum mechanics to create localized errors in space-time. We still have things seemingly to flit into and out of existence, but now, instead of it being a demon that's doing this, it's an alien that has some advanced technology, letting them play with quantum mechanics to phase in and out of our space. Quantum mechanics is fascinating and extremely weird, and seriously, insanely hard to describe mathematically. But unfortunately, it doesn't cause all that much weirdness on the macro scale. And it certainly can't be used to explain away something as complex and strange as our consciousness, or our seeming ability to make free choices. So I wouldn't hold my breath for our evidence of ghosts to come from the world of quantum mechanics. And I wouldn't worry about falling through the floor because your particles somehow all instantaneously began to act like waves. That's it for this month's episode. I'm hoping to be back in like another 2 weeks with another episode, assuming that the holiday writing goes well when I'm in New York for Thanksgiving. As always, you can find me on Twitter, Instagram, Podbean, and Facebook by searching for the Mad Scientist Podcast and clicking on the one that has a jack-o'-lantern for a logo. That jack-o'-lantern logo was designed by Carrie Shaheen. In the future, I'm hoping to not only have sponsors, but also to feature a not yet famous band with some music that they would like to share. My start in performing for an audience, I guess, was as a part of a ska band in Staten Island, New York, and I would absolutely love to help get the word out about you or your friends' music if you have any. And that's to say, if your friends have any music, not if you have any friends. Please send me a message if you would like your music featured. Thanks again for listening.